Hi everybody, welcome back to Chem 140, where today we will be doing more calculations with empirical formulas, more or less. I had a good weekend. I played way too much Final Fantasy 6. I'm about halfway through the game now. I'm not rushing through the game because I'm enjoying it and I'm trying to do all the things, but my party is very underleveled. And I got to the next area of the game, which is world map change, and I'm very underpowered. I had to run away from the first battle. I was like, oh shit, this is not going to be good. That was my weekend. That and little sleep. Because being an insomniac does that to you. So, hopefully you all had a good weekend as well. Today we're going to finish Unit 13. We might even finish Unit 14 also. And that's just 15 and 16 left, and then we're done. So, like, there's not really that much of the class left, which is cool and all, but also kind of surprising because, like, holy crap, where did the quarter go? Well, it's week 9, so that's how it works, right? All right. What's due and upcoming? So lab worksheet number 4 is due tomorrow. Closes on Wednesday, and then quiz number 7, which is for Unit 12, is due Wednesday and closes Thursday. So make sure that you get those in before the due dates, and absolutely make sure that you get them in before the closing deadline. On the screen as a warm-up, I'm going to give you this problem. I don't believe that we did this ibuprofen problem because my little bookmark wasn't set to this page. But just as a refresher on what we did last week, I want you to tell me the empirical formula of ibuprofen using this data. Now, we were doing mass percentages last week. In this case, I've already given you masses. So you do not need to assume that you have a 100-gram sample because the masses are already present. So remember our 3-step process of step 1, find all the masses, step 2, turn them into moles, step 3, write the formula out of the information. Step 1's already done. So go ahead and work from there to get your formula and tell me the empirical formula of ibuprofen. We'll go over the answer in about 5 or 6 minutes or so. So see you in a bit. Let's say 2 more minutes, and then we'll go over the answers. All right, let's go over the answer here. Oops, that didn't quite capture everything. And then there we go. Okay. So I have these masses, and I apparently have purple for my color because I changed it last class. So that's what we'll work in. So 7.568 grams of carbon, 0.881 grams of hydrogen, and 1.551 grams of oxygen. So we've already got the masses. So let's turn everything into moles. You didn't get an integer for carbon. Let's see if I can find the mistake here. So a mole of carbon should be 12.011 grams, right? That's off the periodic table. And I don't know why I thought I was going to do that number in my head, but I accidentally hit enter one keystroke too early, and I got the wrong number. So I get 0.6301 moles of carbon. I didn't select everything. All right. Got to do the same thing for hydrogen here. So there's my hydrogen. I hit the wrong number there, too. Okay, so I get 0.8740. Oops, I only get 3 sig figs. And then for oxygen, 16 grams per mole oxygen, I get 0.09694. I wrote oxygen above. I meant to write hydrogen here. All right. You can't see the number we just did, so let's write this right here. Let me fix this. Let's go back to black ink for a second, just so it's darker. Each 0.874. 0.09694. All right, so there's our pseudo formula. Now, again, no formula is like this, right? Oh. My stream is getting interrupted here. Hold on. Are we back? We're back. Okay. I just happened to look over there and saw that my connection dropped real quick. So, no formula looks like this. So we're going to divide by the smallest number, and that's oxygen. That's this one right here, right? So that means for carbon, I would get 0.6301 divided by 0.09694. And that's really strange. We got 6.5 for that. We'll come back to it, though. We'll see what happens. So H is 0.874 divided by 0.09694. I got real close to 9 for that, so we'll just write 9. And then O is just that. All right. So we have an issue, right? What the heck do I do with this? And so this is a situation that comes up when your empirical formula does not have a 1 in it. So our empirical formula is not a 1 to something ratio. For example, if I had something like this for my empirical formula, when I divide by the smallest number, I would actually get this. Right? Because dividing C2H3 by 2, 2 divided by 2 is 1. 3 divided by 2, though, is 1.5. So if you see a decimal that looks like a fraction, so 0.5 is a good fraction, 0.25 is a good fraction, 0.33333 is a good fraction, what you need to do is you have to multiply to clear fractions. So 6.5 here is the same as me writing this, right? So we're going to multiply the whole thing by 2 to clear fractions. And the result that we get should be the empirical formula of ibuprofen. Let's go look it up. According to Wikipedia, ibuprofen's formula is right there. There it is right there. So not only did we get the correct empirical formula, we got the correct actual formula too, which is kind of cool. So this is an instance, this is why I put this problem in here, is you can sometimes land on a number that represents a half or a third or a fourth or something like that. And that occurs when you have no ones in your empirical formula. So be mindful of that potential possibility. All right, let me resize this for the next time that I need it, because otherwise I'm going to get super confused. That's good enough. Okay. Boop, goodbye. All right. While we're on this slide, what are some common decimals that you should be looking for if you get these as numbers? So let's just write some of these down, just in case they come up. So if you got something like this, then you can clear that by multiplying it by 2, and then so what you would get would be something like this. And then that would be an empirical formula. What if you had something like this? Then that would be times 3. And then same thing like if you had this. You could times that by 4. And so on and so forth. Really, what you're trying to look for is numbers that look like they are fractions in disguise. If you don't land very close to a whole number, like within 0.01 or less or so, that's a good sign that you want to look for a fraction. So like if you were at like 0.16 or something, that could be like 1/6 or 1/8 or something like that. Just try and look for that. I'm not going to give you problems that go past, say, times 5. So if you see like if you saw like, I don't know, something like this, C 1.2 H or whatever, this could be potentially times 5. I don't think that any problems I give you will go past times 5. Just because they are uncommon. That being said, one year I did give my class toluene, which has the formula C7H8. Didn't even think that it would be times 7, and everybody got the wrong answer, and I was like, why is everybody getting this wrong? And then I was like, oh, shit. I almost said the other word, but I wrote the problem without even thinking about it, and yeah. So when do you need to convert to a higher number? Whenever you land on a fraction. So the reason that we're having this conversation is because when we did this process over here, we didn't end up with all whole numbers. We had this weird fractional number. We had 6.5 as one of our results. 0.63 divided by 0.096 was 6.5. So if we had landed on a whole number, we wouldn't have to worry about this. We'd be done. But if you land on a fractional number, you have to clear out the fraction. And so this is something that can occur. Could it be rounded to 7? No, because you're right between 6 and 7. In these cases, when you are dealing with empirical formulas, because you are expecting integers, you only want to round them if you are extremely close to them, and not round out half of one, because that's implying that like you have an issue here where you need to multiply by 2. Because remember, this over here, this is an empirical formula, right? But if I divide by the smallest number, I get a fraction. If I round this to just this, these are not the same thing. So you cannot do that. Don't round fractions when dealing with the pseudo formula. Only round if you are extremely close to an integer. I was drawing all over the screen and you couldn't see that, I guess. There we go. Yeah. So what I said was this right here, C2H3. If I divide by the smallest number 2, I get CH 1.5. If I rounded that to this, I don't get the same result as what I started with. So that would be incorrect. All right. Now, once you have done the empirical formula of a compound, and you have the empirical formula, you are not 100% certain that that's actually what you're looking at. With the ibuprofen case, it turned out that ibuprofen is an empirical formula, and it's actually its molecular formula. But in not on all cases will that be true. So what if you want to find the molecular formula? What you need the molar mass of that. We can do that using mass spectroscopy. We're going to talk about mass spectroscopy in 161 if you're taking it with me. If you take it with any other instructor, I don't think that they cover it very much, if at all. I talk about mass spec because I spent years doing it, and so I know it back to front. And so it's like, oh, I can explain this in 20 minutes or 10 minutes. But because I'm not going to test you on it in this class, I'm not going to fill your brain with extra information. What suffice it to say is that you can weigh molecules quite effectively. And so what we're going to do is we're going to multiply the empirical formula by the multiplier to get the molecular formula, but we'll need to know the molecular, or we need to know the multiplier, right? Well, if I know the mass of the empirical formula, because I know the empirical formula, so I know its mass, right? And I know the molecular formula's mass, I can then calculate the multiplier. So once you have solved for the empirical formula, you can then figure out its formula mass by going to LenTech and typing in the empirical formula. Then you just check the ratio of the molecular mass that I give you by the empirical mass. So let's do an example of that. Let's suppose that I do all of the grunt work. We won't be tested on what? This you will be, molecular formulas. You might be thinking of combustion analysis, which is the next section that we're going to skip. But this I am testing you on. So let's suppose that you figure out the molecular formula of your compound for a given problem, and this is the outcome you get. You get CH. And then you analyze your substance, and you find out that it weighs 78.11 AMU. So let's figure out the multiplier first. So first, what is the weight of CH? What would its empirical mass be? Well, if we go to LenTech, which I got to get on the screen here, so there we go. And all I do is type in CH. So CH. And it told me 13.02. AMU or grams per mole, they're the same thing, right? Okay, how do I figure out the multiplier? Well, the molecular mass over the empirical mass is the multiplier. So that would be 78.11 AMU divided by 13.02 AMU. And when you punch that in the calculator, you should get an integer. And in this case, I got 5.999. That is close enough to 6 to take it. So what I do is I take my formula now, and I multiply it by the multiplier. So if this is the empirical formula, this is the molecular formula. So what we analyzed was C6H6, or benzene. And god damn it, I keep forgetting to do that. There you go. Sorry, you couldn't see what I was doing, because it was hidden behind the screen capture. But hopefully you have the gist of it. So you just need to figure out what the mass is for the substance that you have determined from the empirical formula, then figure out the multiplier, and then generate your result. Okay. And again, yes, I will test you on these types of examples. So I will expect you to get the molecular formula. All right. I'm going to give you an entire problem. So start to finish, I want you to tell me the empirical formula for this data set. And then I want you to tell me its molecular formula if the actual substance weighs 86.09 AMU. Okay? So step 1, figure out the empirical formula. Step 2, use the data that I've given you to calculate the molecular formula. Okay? So go ahead and do these 2 steps. And we'll go over the answer in about 6 or 7 minutes or so. All right, let's say 1 or 2 more minutes. We'll go over the answers here. All right. Let's go over the answers. First, I got to clear my screen here real quick. I selected all in the wrong thing. That's no good. There we go. All right, so I have 27.90 grams of carbon. And I also have 3.512 grams of hydrogen and 18.59 grams of oxygen. So let's do carbon first. We know the molar mass of carbon is 12 grams per mole, 12.01, so. And I get 2.323 moles of carbon. All right, we'll do the same thing with hydrogen. Hydrogen is 1.008 grams per mole. And I get 3.484 moles hydrogen. And then same thing for oxygen, we'll turn it into moles. 16 grams per mole oxygen, so that means that this many grams is equal to 1.162 moles of O. So the pseudo formula that I'm going to get would be C 2.323, H 3.484, O 1.162. I'll divide by the smallest number. And so I get C2 and then that looks like H3, and then O is just O. So there's my empirical formula. There you go. Okay. Now that we've got that, we can go to Lentech and figure out its mass. So I still have Lentech captured here, so I should just be able to do that. And let's type this in. So C2H3O. And it says the empirical mass is 43.04. So let's write that down. Okay. I scrolled it off the screen again. I forgot to turn that off. There we go. So I know that my molecular mass is 86.09. So I'm going to divide it by the empirical mass that I just calculated off of Lentech. When I do that, I get n equals 2. So I'm going to take my formula I just had. We're going to multiply it by 2. And there's the molecular formula. All right, very good. All right, any questions? Let me know. We are not doing combustion analysis, so we're just going to go like this. Do. And we'll just skip it. There we go, hooray. I'm just doing that so that we can do this. I need to actually click on that. There we go. I clicked somewhere else. That's okay, whatever. All right, give me just a second. I will get the slides up for Unit 14. And we'll get started on that. That didn't pop up on my screen. Oh, it did pop up on yours. Oh, and here it is. Okay, cool. I got stuck in some sort of weird loading issue. All right. Chapter 14 is about chemical equations. And what we're going to be doing with chemical equations is more or less just balancing them. So this is a crucial activity in order to get the correct answer. However, it's not technically demanding. So this is kind of a little bit of a breather unit, we can call it. So on the screen, I have an equation. And if I were to put this reaction, A plus B, in a container, so I'm going to seal the container in here, and I've got a bunch of A, and I'm going to react it with B. And I have some mass of A, so we'll say X grams, and then Y grams. When the reaction is done, I'm going to have a product. What would the mass of this be? Well, it'll just be the sum of the two, right? Because, oops, well, it was sealed until I broke it open. There we go. If the container is closed, no matter can escape from it. So the mass of what's inside must just remain constant. Chemistry does not change the mass of stuff. It simply rearranges the valence electrons. The result of that is new products. And so we talked about this at the very beginning in Unit 1. This is called the conservation of mass. When new products are created from reactants, we do not create nor destroy matter. Every last bit is used. Oh, excuse me. And so this is the conservation of mass. Now, a consequence of that is that you just sum up all the reactants in terms of their mass, and that'll be the sum of all the products. That can be helpful depending on the application that you're doing. Now, because matter is conserved, that means that the number of atoms must also be conserved too. Because each atom of a given element has a certain mass attributed to it, right? So therefore, if I have 3 chlorine that go into a reaction and 5 sodium or whatever, I need to get that same amount out as the product, regardless of where they end up. They could end up in different compounds, they could end up in the same compound anywhere. Excuse me. But the total number of each type of atom has to remain constant, or I would violate the conservation of mass. And so what we need to do is take that principle and put it into a chemical equation, and then balance the equation. Now, in order to do that, first we need to understand how to write a chemical equation. Throughout the quarter, you have been taking observations on various reactions that I've linked videos to or have shown videos of on YouTube. And you could describe those in a sentence like the following. So, sodium metal reacts vigorously with water to produce sodium hydroxide and hydrogen gas. Now, that's helpful contextually, but we may or may not want to represent that information in a more condensed way so that we can do work with it. And so that's where this comes in as an equation. And so we get a chemical equation that looks like this. And there are a bunch of different... Oh my goodness. Oh, sorry. There are a bunch of different parts to the equation. And our job is going to be to identify what all these parts are and then manipulate them in such a manner that it helps us accomplish whatever task we're doing. So, first, let's talk about the sides and what this arrow in the middle means. Reactants are usually on the left of the arrow, but importantly, they are always on the tail of the arrow. Reactants always end up at the tail of the arrow, regardless of which direction the arrow is pointing. Generally speaking, we are going to be writing our reactions left to right, because that's the direction that we read stuff in. However, in Chem 163, you will start to see reactions that go forward and reverse. So, I'm just trying to be specific for that, just in case you get to 163 and start seeing an equilibrium error and going, well, Wes said in 140... reactants are always on the left. Well, they're also always at the tail of the arrow. So, if reactants are what you're mixing together to do a reaction, then products are what you produce. They are the result. Products are always at the head of the arrow. And so you always point in the direction of production. Excuse me. So in this reaction, I would react 2 sodium atoms and 2 water molecules. And the output would be 2 sodium hydroxide molecules and a hydrogen molecule. All right, so that's reactants and products. What do the little indicators mean here? I write these as subscripts because it makes them smaller and so they take up less space. However, I think the convention is to write them in just like big. I write them small to just try and condense them down. In the parentheses... Sorry, yawning again. Ugh. In the parentheses, I have included the phase of the substance as an indicator in case you were observing this visually. So S, L, and G are phase indicators that you are familiar with. They are solid, liquid, and gas. AQ is a little bit special. What AQ means is it's dissolved in water. And so what would happen is that this would dissociate into the ions, and each of those would be aqueous. Now, this part is true, that they exist as separate ions, only if it's ionic. If it's molecular compounds can be aqueous, but they don't dissociate. So carbon dioxide can be aqueous for, say, like seltzer water. But we would only write CO2 parentheses AQ. We would not write C plus O or whatever, because it doesn't dissociate into ions. But anything that is ionic and soluble, we'll get to solubility later, we would write AQ after it. Now, these are the four indicators that you're most likely to see: S, L, A, Q, and G. Generally speaking, for the purposes of this class, we won't really write indicators for reactions unless I specifically tell you to do so. On Canvas, it's very difficult to add all of that. Excuse me. So that I will not be requiring you to do that unless I say, like, hey, what phase is this? And you have to type it in like some other box or something. I don't know. All right, the last part of the equation before we take our break here is this number that is in the front. Now, you'll notice that my hydrogen, I have a blank here. I'm pointing at that blank. These numbers are coefficients that are intended to balance the equation. And so our purpose when we get back from the break here is we're going to look at equations where all the numbers have been omitted. They aren't known. We just know what we put into the reaction vessel and what the output was. What our task is going to be is to then figure out the numbers so that we can describe precisely how stuff is behaving in the reaction vessel. Because if I don't have any numbers here, let's say I scribbled these out here. So this 2 and this 2 and this 2 are in here. Then what this would be suggesting is that 1 sodium turns into 1 sodium. That checks out. 1 oxygen turns into 1 oxygen. That checks out. But 2 hydrogen would then be 1 plus 2. And so I'd be creating this extra hydrogen here. That's invalid. We cannot create or destroy matter in a reaction. So this does not react in the form shown currently, where it's 1 sodium and 1 water molecule makes a sodium hydroxide and H2. It can't do that. There's not enough hydrogen to do that. So our task, we're going to do that when we get back, is to try and balance equations so that we get a representation of what's actually going on. All right. Oops, that's from the previous class. Let me erase that. We're going to take our break now. I am going to go chug more water. Hopefully that'll wake me up. I don't drink caffeine, so that's on me. But I'm going to do that. We'll start the timer here. And we'll see you in 10 minutes. All right, I'm back. Let me wind this down here. I swear, my lectures are going so quickly. I don't know where 10 minutes went there. I was talking to another friend in Discord about science, and then suddenly 10 minutes are elapsed. And I was like, why did the timer turn red? Oh, yeah, because I need to do my job. All right, so let's talk about how to translate sentences into equations first, and then we're going to balance equations from those sentences, okay? So if you are given like a statement, and the statement would be something along the lines of like sodium hydroxide reacts with hydrochloric acid to form water and table salt. Whenever you see a compound written in a statement, so for example, sodium hydroxide, you would just write its formula. Hydrochloric acid, just write its formula. We know all these names. We did the nomenclature section, right? So we can write those formulas into our equations. Now, if you are given an element like hydrogen or oxygen or magnesium, how do you write elements? It sort of depends on what form they're in. Most elements are atomic by nature, so all metals we consider to just write as atomic. I'm sorry. We write all metals as atomic. So if I had iron metal, I would just write Fe parentheses solid. If I had mercury, I would write Hg parentheses liquid because it's a liquid. That's how we find it. Gases are a little bit more obnoxious. Some elements exist monotomically as gases and they're monatomic, but others are diatomic. And so here are 7 diatomic gases that exist in nature. These are not the only ones, but these are the main ones that you will see. So if I do a reaction and one of the products is nitrogen gas, then what I need to do is I don't want to write N with parentheses gas. I want to write N2 because that's how we find it. And so these are really just, you have to commit these 7 to memory. You're going to see these 7 substances so often that it is worth, that's not the pen, that is the highlighter. There we go. It is worth committing these to memory, and I'm going to give you a little mnemonic for this on the next page here. These are the silly 7. Phosphorus and arsenic make tetraatomic gases. Don't bother memorizing those. You're not going to need to. In fact, beyond me saying that right there, you'll probably never see that information again. I only know it because I've seen it in textbooks, and I'm like, I guess I'll mention it. I hit the spacebar on accident, and I accidentally muted myself. That was weird. All right. Sorry, I did it again. It's because I keep misclicking, and then I'm like hitting the spacebar to go to the next slide. So thank you for pointing that out. So don't worry about the P4 or arsenic 4. Other gases are monatomic, but the silly 7 are important. We do care about those. Here's how we have arranged them on the periodic table to help with this little mnemonic that I have. So you can see that there are 7 that I've indicated. 6 of them are on the right side there, and they form the shape of the number 7. The backbone of which is in group 17, or 7A. And then why is hydrogen up by itself? Well, hydrogen is silly, that's why. So try and remember these the best you can, that they are diatomic, because it will help you tremendously just having that factoid in your back pocket. All right. So I want you, to the best of your ability, to write all of the information that you can from this statement into a chemical reaction. Try to include the phases if you can. I'll give you a hint. If it's ionic, write it as aqueous. Otherwise, write it as the phase that you think is appropriate. There is one substance in here that does not really participate in the reaction, and thus you shouldn't include it in the reaction. And that is water. Water doesn't react here. Water is just the medium that the substance is suspended in. So try writing out this reaction. Include the phases to the best of your ability, and we'll go over the answers in about 3 minutes. One more minute, we'll go over the answers. All right, let's go over the result here. If I can get the pen to register. There we go. Okay, so we've got aluminum metal and copper 2 chloride. And those are mixing together, and the solution reacts to make copper metal and aluminum chloride. Now you'll notice we're creating chlorine out of the ether here. I had 2 before and now I have 3. Don't worry about that because we haven't balanced the equation yet, so everything is fine. And now we can just go in and put all the phases in. So metals by themselves are probably solid. At room temperature they are. You'd have to heat the heck out of them to get them to be liquid. And then anything ionic would be aqueous here, so we can do that. So this would be the complete reaction here. If you omitted the phases, that's okay. In fact, the best way for me to require you to include all the phases would be for me to give you a giant table of every possible phase for every possible substance, and that's just going to be too cumbersome. So, in reality, it's not practical in an introductory class for me to expect you to include the phases, because there are just so goddamn many compounds. So, don't worry too much about the phases unless you are specifically instructed to, and I honestly can't think of a situation off the top of my head where that would come up. Alright. And again, that's not balanced. We're going to balance it later. Wow, that's a legacy thing. So this is not chapter 15. So this is unit 16. So we're going to more specifically address when do you use AQ versus S in unit 16. All right, I'm going to give you more reactions. Oops. I want you to do the same thing you just did with these 3 statements. Try and include like a plus and an equal. So if you don't want to typeset an arrow, you can use an equal sign as the reaction arrow. That's totally fine. So yeah, try that for these 3 statements. Let me number them for you so you have a number here. 1, 2, and 3. And do the same thing you just did. If you can include phases, go ahead and try and do that. Notice that only the first reaction has water involved, so it's the only one that's going to have aqueous. But also notice that it says specifically reacts with water. So water will be a reactant in that one. Okay? Go ahead and try these. We'll go over the answers in about 5 minutes. Type your result in the chat once you got them. One more minute, we'll go over the answers. All right, let's go over the result here. First, let me clear all that. And then it's not scrolling. Why is it not scrolling? There we go. All right, so we got calcium metal reacts with water. There we go. Oh, I gotta hit that again there. Which is a liquid to form calcium hydroxide and hydrogen gas. I don't know how to write the letter G, apparently. Let's try that again. There we go. So something like that. What's important is that we get the formulas right. Remember that calcium hydroxide is CaOH2 because calcium's +2. Each hydroxide is worth just +1, or -1. So if I dissociated this, I would get that. So these would be what the parts of this are. All right, hydrogen gas and oxygen gas react violently to form water vapor. And so there's that one. That's a fun reaction that I wish I could do for you at the college. In the spring, when we didn't have a pandemic, we would do a science fair where we would invite the public to see both demos from all the different STEM departments and show student research projects that students had done in various programs. So, like when you get to OChem, in Samita's class, she gives you the opportunity to do some scientific research projects on various organic compounds and processes that you've studied. And then in general chemistry, which is what you're taking right now, I give you extra credit to go out and mix things together for fifth graders. And everybody likes this. Like, it's fun to interact with fifth graders because when you're in fifth grade and you see, like, oh, I mixed the two colorless things and now it's blue. Ah. Or you shake this colorless vial and then it turns blue, but only if you shake it. Like, that's cool to kids. Kids love that stuff. So that's always fun. And then at the end, I do my chemistry demo, just sort of as like a thanks for coming out, because I was the first person to do this, and I'm sort of the ringleader now of the science fair. So I do elephant toothpaste, which is peroxide plus a catalyst, produces oxygen, gas, and water, and it makes bubbles and foam, and they all go everywhere. But the one I want to do is hydrogen oxygen, makes water vapor. The problem is that with this reaction, what you also produce is a big explosion. If you do this inside, all the windows would shatter if the door was closed. So I can't do it as a demo in the classroom. And if I do it outside, security would probably think a bomb went off on campus. That's how loud it is. Like, it sounds like an explosion, because it is. So look that one up on YouTube. It's real good. And then this last reaction, mercury 2 oxide, which should be that, decomposes into mercury, which is a liquid, and oxygen gas. My parenthesis got eaten there because my text is bad. There we go. All right. Now, you don't have to balance them just yet. We're going to balance these eventually in a different section. In fact, that's what we're going to do for the rest of the lecture today, is we're going to balance stuff. All right, let's talk about how to do that. Because we don't want to violate the conservation of mass, right? If you cut aluminum on a water jet, hydrogen gas can get released, and you make a nice little boom. I would believe that if you have something hot enough, the aluminum could reduce the water into oxygen and hydrogen. I could see that happening. I'm not exactly sure what a water jet is. I assume it's like laser cutting except with water, where you have like the super pressurized water and you use that as essentially like a cutting device or implement, is my understanding. And yeah, I could see that generating a ton of friction because you're cutting a metal with water. So, yeah, that will heat up real freaking fast. So that checks out to me. 60,000 psi. Okay, yeah, that's definitely what's going on then. Yeah, so you're probably you're heating up water so much that when it hits the aluminum, either the aluminum gets oxidized by the water to create hydrogen gas and oxygen gas, or you're just heating the water to the point where it dissociates into its constituent elements. And then, of course, that becomes explosive too. All right. When we balance equations, we're going to stick numbers in front of them. And then when you use the equations later, you're going to be using those numbers. So it is very important that you check your equation when given one to be sure that it's balanced. Now, I am not going to try and purposely trick you, in the sense that I'm going to give you an equation that is incorrectly balanced and then say, haha, you should have balanced it first. I'm not going to do that. That being said, if I want you to balance an equation, I will say the equation is unbalanced and provide blanks for you to draw numbers into. Draw being a sort of a air quotes word because you can't draw the numbers in on canvas. You have to write it down yourself. Alternatively, I will fill in the numbers for you, and if there is a mistake on there, please let me know, because that would be very bad. But as general like principle, you should always check to make sure your equation is balanced. Just do it really quickly and see, like, okay, does this make sense, or did I create matter? Because if it's not balanced, it's invalid. You can't use it for anything else. All right. The way that balancing is going to work is that we're going to just take inventory. Everything on the left should equal everything on the right. And if there isn't the same number of a given atom on both sides, then our equation in its current state violates the conservation of mass. Therefore, it is not valid, and we need to keep playing with it. The only thing we're allowed to edit are coefficients. So this right here, this is the only thing that you can do. You cannot change the formula itself. So if I have H2O, you're not allowed to just cross that out and write H2 and O2. And then balance them separately. That is invalid. So all of our compounds have to be retained in the states that we observe them in. So keep all of the formulas, keep all of the phases. The only thing you change when balancing an equation are the coefficients in front of each substance. So let's look at an example here. This is the combustion of natural gas. If you have a gas stove, 1, this is the reaction that is happening, and 2, you are very lucky, because electric stoves are shit. I grew up with a gas stove in California, lived out in the boonies, but we had gas stoves, and cooking was wonderful. I hate electric stoves. But methane is a greenhouse gas, and we don't want to have too much methane in the environment. Leaks would be very bad, so there is a push to get rid of gas stoves, and I agree with it because environmental concerns are what they are, but I also hate it. All right. First things first, when you're doing a balanced equation, draw a big line right through your reaction area. Split the two sides into reactants and products. And when you inventory these, so I have a carbon, a hydrogen, and an oxygen. So I'm going to go like this. Carbon, oxygen, hydrogen. I'll line them up in the same way, so it makes it easier to compare. We need to have the same number of both, of all the substances on both sides. So let's tally them. I have 1 carbon on the left, 4 hydrogen, and 2 oxygen. Checks out. I'm just looking at the coefficients here. On the right side, I still have 1 carbon, so that's good. That one's done. 3 oxygen, so that's a problem. And I only have 2 hydrogen, so that's no good either. So now what I need to do is, let me get rid of these little dashes here. I'm going to highlight the space in front of here, of each one. In this highlighted space here, we're going to enter a number. And our task is to enter the correct numbers so that everything is balanced on both sides. Let's just do this color. There we go. Okay. Now, you can input any number you want to in any position. For example, if I were to put, and I'm going to draw it like this, I'm going to put a 3 right here so that I can erase this later. What this would do is I would say, okay, now I have 3 times CO2, so I have 3 carbon. And then I would have 3 times these 2 oxygens per molecule. So I'd have 6 oxygen plus this one over here. So this 3 would become 7. Because now on that side there are 7 total. 6 from the CO2 and then 1 from the water that's left over. Now, if that helps you, great. You've put a good number in there. But in this case, I'm sort of just entering a random number and seeing what happens. That didn't necessarily help me, right? My carbon, which was balanced, is no longer balanced now. And my oxygen is now further away from 2, which is not great. So we're going to go like this and erase everything we did. So there is a rhyme or reason to this. And so the strategy that I recommend that you follow is the following. What is the fate of each element? And so when I say fate, what I mean is, where does it end up? What is the eventual outcome? So looking right here at carbon, I see that all my carbon has to go here. Carbon's fate is to become CO2. It started as methane, but it will become CO2. It can't go anywhere else, right? So what that tells me is that the number in front of CH4 and the number in front of CO2, it's got to be the same because there's 1 carbon in each of those. So if I had a 2 in front of CO2 but only a 1 in CH4, I would never have carbon balanced, right? So now I automatically know, okay, those 2 numbers have to be the same. Likewise, what is the fate of hydrogen? It has to end up here in water, doesn't it? There's no other possible outcome. And so the number in front of CH4 is also linked to the number in front of H2O. But in what way? Well, I only have half as many hydrogen here, so I'd have to put in twice as many. So if this is a 1 to start, then this must be 2. So it's kind of a logic puzzle. Now, if this is 2, what happens? Well, 2 times H2 becomes 4. And then 2 times oxygen becomes 2, plus the 2 that are already over here before. So now I have 4 of these. Did this action help us? Well, in a sense it did. My hydrogen is now balanced, so that definitely helped us in that regard. But our oxygen wasn't balanced, and it made it farther away. However, that could potentially work out in our favor later. Getting off of an odd number onto an even number might help us. And it turns out in this case, with oxygen totally being in pairs, I need 2 more, so I'll just do this, right? And there you go. We've balanced everything. So there's the balanced equation. 1 CH4 and 2 oxygens produce 1 CO2 and 2 H2O. If you have a blank is interpreted as 1. I believe on Canvas, if it asks you to enter a number for something and it's only 1, it will either accept 1 or blank. Do not input blank as 0. Something with a 0 coefficient does not appear in the equation. For example, there are 0 N2s in this reaction. So we don't include them. Only include things that are 1 or more. And so anything with a blank in front of it is a 1. All right, so you've seen it in action. I want you to do the same thing. This is just me walking through it. I want you to do the same thing with this second equation here. So I want you to tell me the coefficients that go in front of each of these substances. This is a little bit more tricky because there's not as straightforward of a solution. But you can definitely get there with a little fiddling. Okay? So I'm going to give you that 3 or 4 minutes to do it. We'll go over the solution when we get back. All right, 1 more minute. We'll go over the answers. All right. So I'm going to walk you through what I would do to solve this problem. So, same thing that we did before. We're going to split the sides up here, and then just inventory. All right. So we know where the nitrogen goes. So this number and this number have to be the same. The oxygen comes from two different sources. So that's going to be a little bit more confusing. However, there's really no great starting point logically unless you come at it from this perspective. I don't have enough oxygen here, so I need to change this number and increase it. I cannot make it 4 though, because I cannot make it 3. Sorry, I can't get them to match. So if I do this, then I have 2 nitrogen and then 4 oxygen because they come in pairs on this side. But when I go over here and put a 2 in here to fix my nitrogen, the oxygen comes along with it and it fixes itself. So you're going to find that with a lot of these different equations that when you balance the equation, doing something will lead you to a logical next step, and then you'll follow the steps to get to the answer. Oops, all that text is on top of mine, so there we go. I do have some other little tricks that you can apply. If you are working with polyatomic ions, so here's a polyatomic ion, write this instead of just P's and O's in your inventory. If you have multiple sources of one of those elements, this can save you a lot of time. And then the second step I've already told you is try and figure out what the fate of your atoms is. And then the last comment that I have is if you have really big numbers, like if you get 100 plus, there's no way that the answer is going to have 100 plus. What that means, if you have like an arms race situation where the products and the reactants just grow and grow and grow and grow and grow and never balance out, you have a math error. If you've made an addition error somewhere, this can happen. And like you forgot to add, like say the O from H2O, and you keep adjusting something different. Then it will just stack forever and ever and ever and ever and ever, and you get the wrong result. So be mindful that that's a thing that can happen when you're learning to do this. And if you just get giant numbers, start over. All right. Now, in the combustion analysis section, I skipped over... Sorry, I'm reading the question real quick. So, in the combustion analysis section, I skipped over an interesting factoid that if you react any compound with C's and H's and oxygen, the only products that you get out are CO2 and H2O. So, if I do this reaction, here's my octane, and I react it with oxygen, these will be the products that I get. Can you balance this equation? Of course you can. I would like you to do that. I'm going to give you 4 minutes to do that. Then we'll go over the answers, and then we'll call it a day because that's all the time that we have. We'll finish doing we'll finish balancing equations because I have more of these on the next slide. We'll do those tomorrow. So go ahead and try this for 4 minutes. I'll check back with you in just a bit. All right, hopefully by now you've made some progress on this. You may have actually hit an obstruction. We're going to talk about that obstruction right here. So I'm going to inventory what I've got. All right. And the first move that you want to make for this is, okay, well, I have 8 carbons. Where do they end up? They end up here. So probably something like this, right? Because now I would have 8 carbon. So that's done. I would then have 8 plus, or 8 times 2 is 16, plus this one is 17. That's an odd number, and that's not great, right? What about hydrogens here? Well, I have 18, so if I do this, now I have 18 on both sides. So my carbon and my hydrogen are all set. Hopefully my oxygen will work out too. So I got 8 times 2 is 16, plus 9 is, shit, right? So now I have an issue. There's no number I can put here that will give me 25. Unless I put this number. Because 25 halves times 2 is 25, right? Now, in reality, this doesn't make sense. You can't have half in O2. That's not a thing, right? But mathematically, this equation is now balanced. What do you think we should do to fix this so that it resembles reality? What's the solution to having a fraction in my coefficient? What do you propose that we do? Any idea? Hopefully somebody's about to send this. How about we just times everything by 2 to get rid of the denominator, right? So if I times everything by 2, then this becomes 2, this becomes 25, this becomes 16, and this becomes 18. And in doing that, all of these would then multiply by 2 as well. But the equation would still be balanced. And there's the answer. Now, if you look at those numbers, 2, 25, 16, and 18, there's no common number I can divide out, right? So if you have to cheat with math so that you can balance the equation by using a fraction, you are allowed to do so, with the caveat that you recognize that no reaction has fractions in real life. You cannot have 4/3 of an oxygen molecule, right? But if writing it as 4/3 helps you, then by all means do it. Then just multiply by whatever the denominator is to kill all the fractions. All right, so you may actually see some reactions written like this, where they have a fraction. And that is a mathematical solution, but not a correct physical one. The correct solution would be something like this. On an exam, I want you to use only whole numbers when inputting your answer. So if you get fractions, again, multiply out the denominator to get rid of the fraction. Canvas would expect this result. This is the answer that Canvas wants for this problem. If you try the top one, it will mark it wrong because I specifically say do not use fractions in your answer. Use integers only. All right. When we come back tomorrow, we're going to do these equations just for practice. You can do them if you'd like. I'll leave it on the screen for like 3 seconds so you can pause the video here if you just want to do this practice before tomorrow. All right. That's probably enough time to pause it. And then we'll go back to this screen, which is, hey, we're done here. Thanks for coming to the lecture. Let's hit this obnoxious little outro music here. What do we got? Lab worksheet due tomorrow. Quiz number 7 due Wednesday. We'll get quiz number 8 up soon. See you tomorrow. Take care.